When graphically displaying a frequency distribution, it's often tempting to turn to a histogram to do so. And histograms are very effective, but they're primarily effective at displaying the shape of the frequency distribution. So thinking about the modality or the skewness or the symmetry. What this misses are going to be explicit measures of, for instance, the location or the variability of the distribution. And this can be quite challenging if you're trying to compare multiple different distributions, right, where you want to know how much variability is in one versus the other, where's the location of one versus the other, and so forth. And so other graphical representations are going to provide effective guidance towards these types of questions that might be lost a little bit with the histogram. It's not to say you can't do it with the histogram, but just that there are easier tools out there. And one of these tools, and probably the best tool for this purpose, is going to be the use of Boxplots, or sometimes called box and whisker plots. So boxplots are graphical displays that are used to summarize a frequency distribution. And the idea with the boxplot is that it provides an easy-to-read representation of the location, the spread, and the skewness of a quantitative variable. And so directly from the boxplot, we should be able to see these different quantities, which really makes it easy to compare across distributions. So what is the boxplot? How do we go about constructing one? Suppose that we have a quantitative variable and it's going to give out observations x1 through xn. The location of these data could be summarized using our sample median. So we could calculate out what is the sample median from these data. Now, if we wanted to summarize the spread of these data, we might use the sample range or the sample IQR, for instance. And a boxplot is going to take these specific values and then graphically display them. So it's going to take the median, it's going to take the range, and it's going to take the sample IQR, and it's going to put those onto a graphic. And so how does that work? Well, the boxplot's going to start by drawing a straight line at the first quartile, so Q1, at the median, and at Q3. So we have three straight lines that are running parallel to one another here. Q1, above that the median, above that Q3. These lines are then connected using vertical lines to form a box that has a middle line drawn throughout it, right? So then we have a box that's going from Q1 up to Q3, and the median is marked across this box. Okay, so that's the box from our box plot. If you look at this box, it's capturing the IQR of the distribution here, right? Because the difference between Q3 and Q1 gives us the IQR. So the bigger the box, the longer the box, the wider the IQR. The smaller, the less the IQR. It also gives us a measure of the location because the median falls within it. Then from here, what we do is we draw out two lines, and these lines are sometimes called the whiskers of the plots, and they're drawn above and below our box plot. And how far do we draw them out? Well, what we do is we draw out 1.5 times the IQR. Okay, and so we go however large our IQR is, 1.5 times above, and then 1.5 times below. But instead of just stopping at that 1.5 times the IQR, right, what we do is we find what is the value of the point that is within this range, either the largest value or the smallest value beneath it. Okay, and we draw the line stopping at that point. Sometimes that's going to be the maximum or the minimum value in the sample, right? If the largest value in the sample is less than 1.5 times the interquartile range above Q3, then we would end up drawing this up to the maximum or the minimum, conversely below Q1, right? But sometimes we're not going to have reached our maximum or our minimum value yet. And if we haven't reached our maximum or our minimum value yet, we stop at whatever the point is that's inside that range that is not yet at the maximum or the minimum. Okay? And so then after those lines have been drawn, if there are still points outside of those, then what we do is we put them represented using dots above or below the line. Okay? So then the sample range can be seen because we're always going to have our maximum and our minimum point represented here, right? And so then if we include the maximum or the minimum, that's going to give us our sample range. We have our IQR from the boxes, and we have our median, okay? The other thing that we can use the whiskers for is by looking at the relative length of the two whiskers. If one whisker is a lot longer than the other one, then that's suggesting that we have skewness in that direction, right? Because then we have values that are going out much further in that direction than they are in the other one. Okay, and so we can see the skewness or the symmetry of the distribution there. Okay, so let's take a look visually at what this actually represents. Okay, so here we have sort of a rough breakdown of what how the box plot works, right? And we start by drawing out our Q1 line right here. I'll use a different color because it's a little bit hard to see. So we start by drawing out our Q1 line, right? Our median line, which will be above that, and then our Q3 line. Okay? And so those are going to be at whatever values we happen to have. And then we enclose those using a box, right? And so we'll put our box there. So now we have this box, and this box represents the IQR and the median both. Then we can go either above or below next, right? So we'll go above the box next, and we're going to start extending this line out, right, up to 1.5 times the IQR, right? And so in this case, this is clearly not drawn to scale because our IQR is this, right? And so we would extend out 1.5 times that value, right? But we stop critically at the maximum value that's within 1.5 times the IQR above Q3. And so what we're saying here is that if you go 1.5 times the IQR above Q3, then we're going to stop at this point, right? Similarly, we go down here, we draw up to 1.5 times the IQR. This one looks a lot more probably to scale down here, right? And we stop at the minimum value that is 1.5 times the IQR below Q1. Okay. Then we can take our points and we say what points exist outside of here, okay? And so if you have any points that are beyond this, then we can work them up here, right? So we have our maximum point is going to be up here, but we have another point outside. And so we place those as dots here. The minimum point actually falls beneath that extended out line down there, okay? And so then looking at this, we can measure out the maximum by looking for the largest point. If there were no points drawn above, then we know the maximum is actually at the end of our whisker, right? We have our Q3, our median, and our Q1. We then also have our minimum point. So a measure of the variability is going to be given by how wide is this box, or alternatively, how wide is the total range that we're seeing here, right? A measure of location is given by the median. And then if you wanted to know symmetry and skewness, we would be looking at, well, what is the relative length of our two whiskers? And so in this case, right, it looks like there's probably negative skew because we have a lot more extreme values down in this direction. So reading all of this information from a box plot is going to be critically important. Okay. So consider an example here. These box plots display the resting heart rates for a group of 150 adults, and they're grouped by their reported activity level. So we have low, moderate, and high activity. And this is where the box plots are going to be particularly useful because now we have 3 different frequency distributions represented on the same graph. This becomes a lot harder to do if you want to use histograms instead. So we can start asking questions about these data. So what is the median resting heart rate for those in the low activity group? Okay, and so then what we would say is we go over to their box, right? We take this and we draw it across, and we see that that's somewhere between, say, 74 and 75, so maybe about 74.5. Median is always going to be the middle line in our box plot. What is the Q1 value for our moderate activity group? So again, we can come over here, we go to the moderate group, right? We take a look at that, and that looks like that's just above 65, perhaps, right? So perhaps 60.5 or so. Just above 65, so 65.5. And then what is the IQR for those in the high activity group? And so for the IQR, remember the IQR is going to be the distance between Q1 and Q3. And so then we take our Q3 value, right? So that looks like that's just above 60. We take our Q1 value, which is a little bit below that, right? And so we could actually sort of zoom in and count out on this, right? So I believe that that's 60. That's going to be 69, 68, 67. So perhaps just a little bit below 67. And then 57 in that case, right? And so we have about a 3 IQR, okay? And so again, these are not going to be exact. Obviously, reading the values off of the charts on the video screen may be a little bit hard, but given the actual charts in front of you, that would be the measures that you're doing, okay? Consider D, which has the largest sample range. Okay, and so here we don't necessarily need to work out the full range, but we could, right? But what we would be doing is be looking at from the maximum down to the minimum value. And so in this low case, we have a single point that's below the whisker down here, right? And so the range is going to include all of that. It's going to go from this low point down here up to that high point here. In the moderate case, we still have this extreme value below, so it'll be down from here up to here. And then in the high case, we actually have a value that's below and some values that are above. Okay, and so just even looking at this visually, right, we can quickly see that the range is going to be the largest on the low, and then on the moderate, and then finally at the high, right? in order, those are the lengths of those ranges. You could work out what they are specifically. And so the low is going to be going from about 59 to about 89, so around 30. The moderate's from about 53 to about 76, so it has a range of about 23, and high is from about 52 to about 71, and so it's going to have a range of about 19. Now, what can we say about the symmetry of each group? Okay, and so with our symmetry, right, we're thinking about this as, say, both symmetry in the tails and then symmetry throughout the rest of the distribution. And so for our tails, if one whisker was a lot longer than another whisker, so say we had something that looked like this, right, then we would know that there were skewness there. But if the tails are about the same length, then it means that the tail behavior is going to be approximately the same in both directions. And that's true for each of the groups here, right? The tails aren't a lot different in either way. And so we can say, well, the tail behavior is about symmetric. And then what we would be looking for is the medians. Are the medians approximately halfway between the Q1 and the Q3? And if so, then you have about symmetry throughout the rest of the distribution here. And while in some of these groups, so for instance, moderate, this is going to be a little bit too high. In the low group, that's probably a little bit too low. In all of the cases, it's not super extreme. And so I would say that all of these are roughly symmetric distributions, right? Because the tails look symmetric as well as the sort of body of the distribution. And so we have approximately symmetric. We certainly have no skewness, and we have approximate symmetry here. Now, we have another example here, and this is going to give us the plant growth based on different types of soils used. And all we want to do here is compare and contrast these distributions. Okay, and so we have soil A, B, C, and D. Each of them displays how much the plants grew based on them. And so we can start thinking about what we can say about the different distributions. And so it's always good to start with one of the traits. And so I'll pick the location to start with, right? And so what can we say about the location? Well, soil C is going to have the highest location, right? Followed by soils A and D, which have approximately the same, followed by soil B. And so we're thinking about the median there. And so the median growth for soil C is going to be the highest, followed by A and D, which are about the same on median, and then soil B has the worst median growth. We could then think about, say, the IQR, right? The IQR is going to give us a good, robust sense of the variability. And the smallest IQR is certainly soil C here, right? Followed by soil A, followed by soil B, followed by soil D. And so based on the IQR, based on the typical values near the center of the distribution, we're going to have C being the most predictable, and then A, and then B, and then D, right? So D is going to be the most variable in this case. But what if we thought about characterizing the total range instead, right? If we're looking at the total range, well, now suddenly A is going to have the smallest, right? Because we're going from our maximum and our minimum there, right? And then we're probably looking at B here, right? So B is going from here down to here. And then whether it's C or D is going to be hard to eyeball. I would say that probably C is next, right? So C is going to go from here to here. And then finally D, which goes from all the way up here down to there, okay? And so D is still the most variable, but we go from C being the least variable in terms of the IQR to being the most variable, or one of the more variables, in terms of its total range. And so what does that tell us about C? Well, it tells us that C is mostly concentrated in a very narrow band, but there are a few observations that are extremely different from the other values. Whereas something like A, right? A is sort of moderately variable, but it never gets too far from that. So we have smaller tail behavior, right? The other thing that we could think about is our symmetry or our skewness, right? And so A is an almost perfectly symmetric distribution, right? From everything we can see, A looks basically symmetric. Same thing with D, right? D has these two sort of high outlying values, but those are only 2 points out of all of the points that we have represented here. And so if you ignore just those 2 points, then of course D is almost perfectly symmetric as well. And so I would say that there's a good symmetry there, especially when you compare this to B or C, right? With B, we have far more extreme positive values, right? We have this positive tail behavior. And then with C, we have this strong negative tail behavior. And so both B and C are going to be skewed, and B is going to be skewed positive, right? So if we're thinking about what that histogram looks like, it's probably something like that. And if in C's case, we're going to have sort of the mirror image of that, right? Something like that. Okay. And so what does this all tell us? Like, what can we summarize here? Well, A is going to be a very predictable and a reasonable growth rate for it, right? In some sense, A is going to be just a very steady soil to use. Never are we going to see things that are too extremely positive, but we're also not going to see things that are too extremely negative. It's low variability, and it has a predictably high median. Soil B is going to typically be a very bad soil if we want large growth rates, right? But it has this positive skew. So there's something that can go on. There's some traits that can go on where sometimes B performs quite well, or at least comparatively well to the other distributions. But on the whole, B is a fairly poor performing soil. Soil C is going to be almost always a predictably very good soil, right? There is this very positive, it's larger than the others in terms of its median, and it's almost always going to be very predictably in this range. However, occasionally we see soil C having these tremendously low negative values, okay? And that's going to sort of be either a case where we might want to look into what happened on these 3 different trials in our growth, right? Why was that so bad? Or it might be telling us something about soil C. Perhaps there's some other condition that if soil C has this other condition met, it's going to be really bad for the plants. But on the whole, it's pretty good for the plants. Soil D is going to be a fair performer, right? It's going to have a reasonable median, but it's very highly variable. Sometimes it performs way better than any of the other soils. Sometimes it performs worse than most of the other soils, right? And so with D, there's a lot of spread there. We don't really have a good amount of predictability about what it's going to be. And so D has both the chance of being one of the best soils, but also a chance of being one of the worst soils, okay? And so we can take a look through all of this, right? This is all sort of summarized here, all the points we talked about. So we're comparing their medians, their IQRs, the ranges, right? The highest maximum values or the lowest minimum values, symmetry versus skewness, right? And then we can think about summarizing what this actually tells us. So soil A being predictable with moderate growth, B typically performs poorly, although it can be competitive with the others. C almost always performs better than the others. However, it can also perform terribly. Soil D performs moderately on average with lots of variability, ranging from very poor to very strong, right? And so reading those box plots tells us a lot about these different soils. And depending on what we needed the soils to do, we could then take this information and use that to inform, say, the choice of soil for growing our plants. Okay, so box plots are going to give us this compact representation of the shape, location, and spread of a distribution. They're easy to compare across different distributions. They're rich in detail, and that makes them widely applicable. You lose some of the information that you might have in a histogram, but you gain this easy to compare, and you gain this explicit encoding of both the variability and the location of a frequency distribution, which makes them highly effective tools that are useful in a great number of different circumstances.